Okay, let's do another one. So here's our p of n. X to the n minus y to the n has a factor that is y minus, or x minus y, and it's for positive integers. So when we do this one, our first case is going to be p1, and that's just x to the 1 minus y to the 1, which is x minus y, which is obviously has this as a factor. So we've proven the first case true. So now we can say pk is true, and pk is x to the k minus y to the k has factor x minus y. Once again, k is positive integers. So if that's true, now we're going to prove that p of k plus 1 is true. And so we're going to say x to the k plus 1 minus y to the k plus 1. And we need to prove that that has a factor of x minus y. So the first thing we can do, we can say x to the k, x to the 1, minus y to the k, y to the 1. Now our goal is to try to make something that looks like pk. And so it would be nice if we could just factor out this x and this y, and then we'd just be left with x to the k minus y to the k. We can't do that though. That's not how factoring works. And so what we're going to do, we're actually going to inject something into this problem. So I'm going to try to keep this as clear as possible because it's definitely something, it's kind of a weird technique. Okay, so I'm going to color code it. So that blue stuff is the same blue stuff. But what I'm going to do, I'm also going to add y to the k x, and then subtract y to the k x. Now the reason why I did that is because now I can group these together. Oh, whoops, that's not the order I want to do it. I want to switch the order. I want this to be the minus 1 and this to be the plus 1. The reason why I'm doing this is because now I can just factor out an x, and when I do that, x to the k minus y to the k, and then I'll rewrite this stuff. Alright, and over here I can factor out a y to the k. Alright, and we have almost proven this. So, since pk is true, we know that this has this as a factor, and this just times by whatever x is will still be divisible by this, so it's therefore a factor. This over here is the same thing, so it's definitely divisible by that, or it is a factor, and so therefore we have proven pk plus 1 to be true. And since pk was left kind of open, we could start at p1, and we know that p2 is true. Now, because we know p2 is true, we could start at p2 and then go to p3, and we could do that to infinity. So that one is done. Alright, we still got a couple. We got a lot, actually. Okay. So now we got to prove and then n is contained on positive integers. Okay, so all we're doing is squaring all the natural numbers and then adding them together. So we just need to prove this to be true. It's generally a good rule of thumb to test it and make sure it's at least true, and convince yourself, like inductively, like using inductive reasoning, that it's true. and then to jump in. But since the book is telling us to prove it's true, I'm going to assume that it probably is true and just jump in with the mathematical induction. So this is going to be our P of n, and then we're going to plug in a 1. And if we plug in a 1 on the left, we get 1 squared. If we plug in a 1 over here, we get 1, 1 plus 1, 2 times 1 plus 1, all over 6. The left side is 1. This is going to be 1, then 2, then 2 plus 1. Yeah, 2 plus 1. It's going to give us a 3. 3 times 2 times 1 is 6. And that's a true statement. 1 is equal to 6 over 6. And so we know that the first case, P1, is true. Now, what we're going to do next is do our PK. So we're saying PK is true. And PK is just the case where we switch all these n's to k's. And so I'm debating whether or not I want to just write it out, but I probably should. Yeah, let's write it out. So I'm actually not going to write this part out, but I'm just going to say that 1 squared plus 2 squared plus 3 squared plus dot 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 and squared, or k squared, k plus 1, 2k plus 1, all over 6. Now, we're assuming that's true now, and then we're going to prove p of k plus 1 is true based on knowing that that is also true. So, p of k plus 1 is going to be 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared plus 1 more, which is k plus 1 squared. And then on the right side, all the k's are going to turn into k plus 1s. Need a little bit more room. Alright, this looks really messy. Now, what I like to do, I actually like to put this one on top of this one. So I'm going to, let's see, I'm going to take it. Why can't I do that? See if I can get that. I write a little slanted, so. Alright, let's copy that. Let's put it up here. No. Alright, maybe I just have to rewrite it. The reason why I like to put it up there is I like to take the blue one and subtract the pink one from it, and it works a little bit better in my brain if I put that one on top. But maybe a better solution is just take the top one and write it below it. So okay, so 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared is equal to k times k plus 1, 2k plus 1 over 6. Okay, so I'm going to subtract. So the blue, so the yellow from the blue. So these cancel, cancel, cancel. Those all cancel. These cancel. And then we're going to get k plus 1 squared. Then on the right, we're going to rewrite the top. K plus 1. That's going to be a k plus 2. this is going to be, if I distribute 2k plus 2 plus 1, so that's 2k plus 3. That's all over 6. And then we're going to subtract k plus 1, 2k plus 1, all over 6. Okay, so if we can just prove that these are equal to each other, then we'll be done. So basically I just need to simplify the right hand side, and it should simplify to k plus 1 quantity squared. If that's true, then this would be true. So there's a lot of multiplication that goes on here. So I'm just going to multiply these first two. So k squared plus 2k plus k plus 2. So that's just multiplying these two together, which if I simplify that, looks like that. Then I'm just going to write the rest of the stuff around it over 6. Okay, now I'm going to multiply this out. So that's 2k cubed plus 3k squared plus 6k squared plus 9k plus 4k plus 6. And then if I simplify that, 2k cubed, these two add to make 9k squared, 13k plus 6. Alright, and then that's still just over 6. Okay, so what I did, I simplified this into this. Now I'm going to do the same thing over here. So I'm going to distribute a negative k to both of those. So I get negative k squared, negative k, 2k plus 1 over 6. Now I'm going to distribute this, so negative 2k cubed, negative k squared, negative 2k squared, negative k, and if we combine those, we get negative 2k cubed minus 3k squared minus k all over 6. Okay, since both of these are over, once again, this came from this. Okay, they're both over 6, so that means we can combine like terms. And it looks like some stuff's going to cancel. So that, we'll cancel that. 9k squared minus 3k squared is going to be 6k squared. And then 13 minus 1 is going to be 12. And then we just have plus 6, and that's all over 6. All of those are divisible by 6, so I'm just going to divide each one by 6. And we end up with k squared plus 2k plus 1. Now, remember, we're trying to make it look like this. So if I just try to factor this, I'm going to get k plus 1 times k plus 1, which is k plus 1 squared. And we just proved that p of k plus 1 is true. So if that's true, based on p of k being true, we've proven the entire initial statement to be true. All right. Yeah, I think I'll stop the video there and break this into another part.